Hi, linear algebra students. So this is the last example in column spaces, null spaces, range, and kernel. And if you understand the theorem, the last theorem that we have covered in class in this section, which basically says that if we are given a standard matrix, the range is the column space of A being the matrix, and the kernel is the null space of A. Then you're all set. Like, you can do this example by yourself. You don't really need the video. You should just use the video to check your answer, right? But otherwise, it's meant to be followed along, right? Like, you try the example and you follow along the video as you do it. So we are given a transformation from R3 to R3 defined by this. Okay, and we are not told that this transformation is linear, but we will actually prove it in the process, you will see. And so that's it. This transformation, I'm telling you, it's linear. And what we want to do is to find a spanning set for the kernel of this transformation. Okay? And before we continue, I want to tell you that this method will be the exact same method to find a basis for the kernel of T, because the spanning set that the vectors in the spanning set that we will find will turn out to also be linearly independent. So let's actually so this method also gives a basis for kernel of T. I want you to see here section 4.3. Okay, so as you look at this video, we will probably have started the concept of a basis. So so keep that in mind. All right. Well, what was the theorem I was talking about? Well, this is just a reminder from the class. So reminder. Okay. So if T is linear and has a standard matrix, A, then it means that the kernel of the transformation is actually the null space of the matrix A. Okay? So knowing that, what is our angle of attack? So number one, we will prove that we will find the standard matrix for the transformation. And in the process, we will also prove that the transformation is linear. So how do we do this? Very simple. We look at this. And the transformation is taking the vector x, y, z and outputs the linear combination of these three vectors using the weights, like the inputs as weights of this linear combination. And the idea is to turn this into a matrix multiplication. So all right, let's do this first. So find standard matrix. So here we go. So here, don't use, if I'm not telling you that the transformation is linear, it means you cannot use the method of like T of E1, T of E2, T of E3, because you don't know right off the bat that it's linear. That being said, we have another method to find the standard matrix that also proves along the way that the transformation is linear. And the idea, okay, let's write first the definition. Okay, so nothing peculiar here. I'm just copy pasting what's on the top. But what I want to show you is that using the definition of matrix vector product, what we get is that this is the same thing as writing like this. Actually, the matrix vector product is the linear combination of the columns of the matrix. So I will actually write them as columns like this, using the entries of these vectors as the weights, right? X, Y, Z. So what did we prove? We proved that there is a matrix that implements the transformation. So let's actually call this matrix A. Okay, so this is the matrix that we're looking for. So this matrix is A. So we proved that there is a matrix that implement the transformation, and this is enough to prove that the transformation is linear. So since T of x is equal to AX, T is linear with standard matrix A. Okay. Furthermore, this now that we know this, we're allowed to use that fact. So we know that its kernel. Yeah, let's actually write here. Kernel is the null space of that matrix. So what this means is that we just have to find a spanning set for null A. So we find a spanning set for null A. Okay, so this is the end of step number 1. Now I have everything I need here, so I'm going to erase the statement. So to find a spanning set, it's we use the same method as what was covered in class. So let's actually write this spanning set for null A. So how do we do that? Well, very simple. X is in null A. So X is an element of null A if A times X is equal to 0. So what it means is that so X is or let's actually write U, okay, instead of X here, just to be more clear. U is in null A if A times U is equal to 0. So in other words, if U is a solution to AX equals 0. So in other words, this tells us, okay, well, solve this, right? So solve AX equals 0. Now we know how to do this, right? We just write the matrix. So we have like -3, 1, 2, -1, 0, 1, and -2, 2, 0. And we augment this with a column of 0. So that is the augmented matrix. All right, I don't want to waste time to row reduce it in this video because that's really not the focus. So I did prepare the row reduced row echelon form. So this is the RREF, which is 1, 0, 0, 0, 1, 0, and finally 2, -4, 0 with this column of 0. Now you can read the solution out of this. So you know, for instance, that all right, this will be our parameter t, and this is also z, right? It's the letter z that's equal to t. And we can read the other variables from their rows, like from their pivots. Okay, so this you will read for x. You will read for x here, and you will read for y here. So what does it mean? All right. It means that so xyz. So x, which is equal to xyz, is equal to, and now that's the t, okay? So reading the z first, okay, we see that z is equal to t, so we put the 1 in this entry. And then reading x, so we know we have 0, but we push the negative 2t on the other side. So, well, we push the 2t on the other side, so we get negative 2t. And finally, with the y, okay, so same thing. Y is equal to, then you push the negative 4 on the other side, and you get 4t. So this is your solution. And let's write here that t must be a real number. Just so that we are clear, this is all the solutions. This represents all the solutions. Okay? So, all right, what did we find out? We found out that U is in the null space of A if U is a linear combination of this vector, right? So, U is in null A if U is a, well, I should say like if and only if, or let's just say if, if and only if, okay, just to be like crystal clear here, that it really goes both ways. So U is in null A if and only if it's a linear combination of this vector, of the vector, and I'm going to write it as a column, no problem with that. So negative 2, 4, 1. Okay? So what does it mean? Well, now I will erase this part. So it means that U is in null A if and only if U is in the span of this vector. And what this sentence means? Well, it means an equality in the two sets, right? It means that null A is the span of this vector. So negative 2, 4, 1. Okay? But now, okay, well, it's time to conclude properly. Well, we know that this is the same thing as the kernel of our transformation because of the theorem that we have seen in class, right? So, all right, the spanning set turns out to be just this set. So this is pretty much the conclusion. So let's write it underneath here. The set negative 2, 4, 1 is a spanning set. And I just want to pinpoint again that it's also a basis. Of the kernel of T. And this is our final answer. Before I close this video, just a quick summary. So what did we do? Well, if a linear transformation has a standard matrix, you can find a spanning set for its range and its kernel by looking at respectively the column space and the null space of its standard matrix. So it's always like, okay, find the standard matrix, find the spanning set for the null space of that matrix, and it will be the same spanning set for the kernel of the transformation. All right, I hope this helped. See you either in class or in the next video.